Welcome to part 1 of the module that describes patterns and frameworks for service access and communication. In this part of the module, we're going to summarize many of the accidental complexities that are associated with the Sockets API. If you go back to section 1 of the course, we have a whole module that describes operating system programming mechanisms, and there's further discussion about the various capabilities in sockets. We'll start with a brief recap, and then we'll give a critique of some of the limitations and accidental complexities associated with the Sockets API. Sockets were originally developed as a C-level programming interface to the TCP/IP protocol suite in so-called BSD Unix. And even though we're going to provide a somewhat thorough critique of the Sockets API, I want to emphasize that Sockets played a transformational role in allowing the internet revolution to occur. If we hadn't had a way to program TCP/IP as conveniently and as portably and ubiquitously as sockets, we might not have many of the things we take for granted today. As proof of this, sockets are available on almost all operating system platforms today. The Socket API has roughly 24 or so functions in it, give or take, as more sophisticated protocol capabilities have come online, things like IP version 6. The API has expanded a little bit, but those are the basic 24 or so methods that we'll see. You can take a look at this URL to find out more information about the Socket API, and there's lots of good books on the subject as well. A socket is essentially an endpoint of communication. What that means is it's a user-level integer or handle of some kind, sometimes implemented as a pointer on some platforms, that provides access into some kernel-maintained data structures. And those data structures keep track of the state of the protocol machine. They buffer information that goes in and out of the protocol stack and are used to set various options and other mechanisms to control the way in which the protocols work and communicate between various endpoints. Most commonly, a socket can be bound to local and/or remote addresses, and we do this in order to be able to communicate via protocols like TCP/IP using port numbers and IP addresses. And we also typically use sockets as a way to carry out some kind of reliable bidirectional byte stream communication link between senders and receivers. So for example, if you go to my website, you'll be using sockets typically in your browser, and those will be accessing sockets running somewhere in the cloud, in the web server, in the data center that serves the web pages from my home site. With those details as background, now let's go ahead and kind of look carefully at what's going on with sockets. There are lots and lots of accidental complexities in this particular programming interface. One of the main problems is it's not very well structured, it's not very uniform, and it's not very portable, even though it's widely available on different operating system platforms. Some of the issues here, the API itself is rather linear. It's not hierarchical. It's hard to tell by looking at the list of 24 functions which ones play which roles in connection establishment, passively or actively, which one play different roles in terms of communication once things are connected. There's not even really any consistency with the names. There's no common prefix, for example, to tell at a glance this function is part of the sockets interface. Some other problems, it's not very portable, and it's also error-prone in addition. The function names and semantics tend to differ on different platforms. For example, on POSIX platforms, send and receive can be used both for file I/O and socket network I/O. On Windows, it can only be used for the network I/O, not the file I/O. You have to use different calls for that. Likewise, some old versions of real-time operating systems were a little quirky, and if you didn't pass in an actual address parameter to the accept call, they would crash. On more civilized operating systems like Windows and Linux and Unix, you don't have to worry about that. It'll handle that case correctly. Some other problems, there's issues with the way in which we represent socket handles. Sometimes, on some platforms, they're represented as integers. On other platforms, they're represented as pointers. This can be confusing. This can be non-portable. And one of the other challenges you sometimes run into is that different platforms put different socket functions and data structures in different header files, which means you have portability issues to work around. There are yet some other problems. There's issues of type safety. Because we're using these low-level I/O handles like pointers or ints, there's issues where the compiler can't tell you at compile time that you're using various functions in the wrong way. For example, there's nothing to stop you from trying to make an accept call on a data mode socket. Likewise, there's nothing to try to stop you from doing a read or a write call on a listen mode socket, both of which are incorrect, but your compiler can't catch that at compile time. There's also a fairly steep learning curve to try to make sense out of the APIs. There's a bunch of different capabilities for address families and protocol families. They're fairly consistent in terms of always going together, but you have to keep in mind which world you're dealing with. Am I dealing with a protocol? Am I dealing with an address family? And it's complicated and error-prone. Another set of problems arise when you start to use some of the options for less frequently accessed functions. Things like multicasting, broadcasting, asynchronous I/O, non-blocking I/O, urgent data delivery. These are confusing. They use ioctl and various socket option parameters. They're not very portable, hard to understand, and so on. There's a number of other very low-level, tedious, and error-prone details. Forgetting to set the port numbers into network byte order is a common one. Forgetting to zero out a socket adder address structure before you use it in a bind call or connect call is another problem. Omitting calling certain functions, like forgetting to call listen before you try to call accept. Having mismatches between the protocol and address families because they're decoupled and separated in terms of their API capabilities. These are all very common problems with sockets. To make this a little bit more concrete, let me give you some examples of problems I've run across when writing sockets over the years. Most of these problems, by the way, will not be detected by your compiler. So here's a little piece of code. It's an echo server example. There can be differences in header files. They may not all occur in the same place, so you'll have to deal with if-defing them somehow. It's easy to forget to zero out the socket address structure, in which case you'll have little garbage values in the interstitial portions between the fields and the structure, which will cause various problems. Here we're using a non-portable data type. We're using an int, which won't work on Windows because sockets aren't really ints on Windows platform. Here's a case where we're making a call to the factory function socket, but we're passing in sock dgram instead of the sock stream that we intended to use. We're now using a check for a non-portable error return value, checking to see whether the result that came back was -1, which is incorrect. We have a mismatch between the protocol and address family. We used the protocol family of the Unix domain, but the address family of the internet domain. That won't be caught by the compiler. We may have the port number in the wrong byte order, depending on what kind of hardware platform we're running on. In this particular case, we forgot to zero out the address structure, and now we're passing it to bind, which will cause all kinds of strange behaviors. We forgot to call the listen function call before we call accept. We're calling accept on a socket that's been set into the sock dgram communication type, which is very confusing and subtle. We're ending up reading from the wrong handle here. We want to be reading from a data mode handle, but instead we're reading from a listen mode handle. And the final problem here is that there's no guarantee that n bytes will be written when we do a write operation due to the issues of short writes and short reads. So how do I know all these problems? Because after many years of programming at the socket API in C, I probably stumbled upon each of these at least once. And along the way, it convinced me there must be a better way to program. So to summarize this particular part of the module, the native socket API has a number of problems. It's tedious, it's error-prone, it's non-portable, it's not very uniform, which means there's more work for you as a developer. These analyses we're doing here have focused on sockets because that's the emphasis of the course, which is on communication. But be aware that you could apply more or less the same critique to many, many other parts of native operating system APIs written in C. The process and thread management portions, the dynamic linking portions, various things having to do with memory management and virtual memory management, other types of IPC mechanisms, and so on and so forth. If you take a look at the URL at the bottom of the slide, here's an article I wrote about over 20 years ago describing some of these issues, and they're still relevant today. One of the main things that's happened over time is that people have begun to use higher level languages and higher level abstractions like middleware to abstract away from lots of these issues. And that's a good thing because it puts us in much better shape to write concurrent and network software that will be correct, easier to maintain, and easier to port to different platforms.